So good afternoon. It's always a bit difficult to be the last speaker of the day. So thanks for staying, and thanks to the previous speaker for introducing quite well the things I'm going to also talk about. The title of my presentation is Data Quality from Tracking and to Archiving with No Gaps, and I have two main topics. The first topic is actually interference, because for any product you want to get out of GPS, is either for scientific applications or for educational or even for commercial application, you need to get data to be able to use them. But at some point, these data have to go to a server, and there are problems also sometimes they are in the file transfer. So I'm going to talk about these two topics, and I think I'm going to cut on few things about interference, because I think we are all convinced that interference is a big threat. GPS are weak signals. They are fighting to share the spectrum with some other bigger and more powerful signals, notably, especially in Japan and in the US, the LTE communication with Docomo and Licado that used to be the light square, but also on the other side, L1 has the Inmarsat guys that are too close to be liked to the spectrum allocation. And there are several different types of interference. We have narrowband, say 1 to megahertz, wideband, larger than that. It can be continuous, it can be pulsed, it can be intentional, people that want to jam you, and they are out there, or unintentional because of, indeed, like we already said, spectrum allocation. And we heard it also before, we can expect interference to be in the GNSS band, but also outside the GNSS band. What do they do to your data? If you're looking at daily processing, you can, if you have interference, you can forget to have complete data. So at some point, you have to go back, do some data and editing, and check out what was affected, and keep on the other end, on the positive side, what was left. And of course, these affect your accuracy. If you look at the kinematic processing, it's people that want to deliver correction for RTK, or if you're doing some PPP, things get even worse because ambiguity fixing, you can forget about it depending on the type of interference. And for PPP, we all know it has to convergence. If you are interrupting the convergence cycles, is not fun to recompute it or to reconverge. And this is an example of what could a potential jammer sitting on the roof of this building do to a reference station. So this is a 10 milliwatt jammer with some realistic antenna parameter simulation. So it would be a radius of 400 meters for a reference station, meaning no supplying differential correction, but also gaps or no RINEX data. If you are a rover in that area, you don't fix because you just don't get signals. And this is, of course, without mitigation. The old school troubleshooting, I think by now, and I'm very happy that not only Septentrio but other manufacturers are taking measurements so that you don't have to go around with a van with a spectrum analyzer and do all the horrible thing we had to do. And I'm very happy to hear that this is a problem felt in the community. So not only Septentrio, but more and more other manufacturers are coming up with solutions that can live together inside the GNSS receiver. There is, of course, much more than visualizing interference and detecting it. There is a lot to do with mitigation. I think it was already told a couple of times. This is a spectrum allocation in the US to give you an idea with a little zoom on what it is around the GPS, and simplified here to have a look at who are the usual suspects that gives you troubles when you are working with GNSS. You have some overlaps on some bands, and notably mainly on the L2 and L5, and of course the most coming L6 and E6 and B3. But also you have, and we heard it also before, harmonics that can go and come from, for example, in UHF or other links and go and sit where you didn't want them. There is aliasing also in the L1 coming from the L band or coming from satellite modem communication. And this is an example of how crowded it gets close to the L1. L1 is typically fairly well protected, so no other people are emitting there or transmitting there, but there are people that are coming close together, close to it from one side and to another. So you need to sharpen the front end of the receiver if you want to do something like that, and avoiding antenna, the complexity of antenna filters. So a bit like we heard in the previous talk, you have out-of-band interference, and to defend your measurement from that, you can do a lot of things, and one is, for example, design the front end of the receiver with multiple demodulators so that you are clearly isolating the L1 component versus the L2 and so on. And that helps, for example, if you are knocked out on L2, you are not going to be knocked out on L1. And of course, in terms of in-band interference, you can notch it out with one or multiple filters, and you can also protect your receiver from wideband type of jammers, like these typical cigarette lighter jammers that are sweeping the band and changing frequency in a fairly large portion of the spectrum. There is another thing, but there is also pulse blanking that is mainly critical when you're looking at DMEs or measuring equipment in the vicinity of airport, but that's typically on the L5 and slightly less detrimental of what happens typically on the L1 and L2. And again, similar to what we have seen, but these are actually field cases. I have a number of examples of what actually happens to your receiver when there is, for example, in this case, a radio amateur digipeater. You have in the top part of the of the picture what was the situation before notching it out. So you had a significant 90 dB emitter that could be relatively easily notched out with one single filter, and this was somewhere in Holland, at Hilversum. The next one is funnier because it was actually the moment where we decided that one notch was not enough and you needed more than that, because you see that monster on the left side, you don't notch it easily, and if it's sitting too close to the frequency of interest to be able to chuck it out completely with a wide band. So you need a number of digital filtering that just tries to reproduce the main peaks, and actually that's a bit of an over-notching with a double notch, but this fixed the problem, and the effect was that the reference station was not able to transmit correction to the rovers, and there was basically a field of pharmacy trying to work that couldn't work back then, and it was affecting both GPS and GLONASS. And other examples here are from closer to where my company is and where I live, so from Belgium in Ostend, again, and broadband amateur TV, and you see in terms of C over N or what you could do before and after, actually after and before the mitigation. And then there are a lot of other things that I just want to show you, and a few more examples of what we have seen out there and how it looks like and how it can be mitigated. This is our radio location devices in the L2 that looks fairly ugly, and this is not typically notchable. You need something a bit more powerful than that. And this is another one very interesting with an amateur radio on the GLONASS L2, and also with some funny mirroring effect, and even worse than that, some saturation on the band. Also, all these recoverable with some what we call our toolkit is named AIM+, so a combination of notch and wideband filtering. This is an example of what I was saying before of pulse blanking together with notching, and this is a typical situation that you come across in proximity of airport and in effect in the GPS L5 and the Galileo. So this is as far as it looks like for what is in the field, there's a bit of a catalog of what we have seen in the past years. There are also the Chirp Jammers, the one that I simulated to be on top of our roof at the moment, and that's the way it looks like in the spectrum domain and in the time domain. We were talking about something that is 10 milliwatts, but if you go to Alibaba or this type of website, you find stuff that is actually at the watt level, and with the power distribution this on the different frequencies of GPS. And this is a small video, if it works, that shows how the interference looks like. And what the notch filters and actually the wideband mitigation is doing. And you see also how the distribution of the I and Q samples is affected, and this is in the time domain. What is kind of cool, and it came in one of the latest updates, is that you not only see the interference before the mitigation has taken place, but you also can see the BB sample, the baseband sample, after the mitigation has taken place. So this is quite interesting, but I picked. I've been working in the past years in our technical support, and we see a lot of things, and a lot of things that look like interference, and sometimes actually what you are seeing that looks like interference is not interference, but is a broken LNA of your antenna. So there are a couple of things that you can do by using interference mitigation, interference visualization, to come up with an understanding of what is the source of the interference. So typically, this is how an antenna looks like in a very simplified way, together with a polaric file. You could take virtually any other receiver, and you have reflection wave that come back and go to the antenna. If the LNA is going funny, you would see something like this, so a peak that you would assume it's interference, but if you start playing with the automatic gain control of the receiver, you can isolate fairly well that this is not an external event, but it's something that is happening between the antenna and the receiver, and since there is nothing that looks like that in the receiver itself, you can make a conclusion and go to your field campaign bringing a spare choker instead of a spare receiver. So this is all working fairly nice, and you got your data, and you have covered the corners, and suppose there was no other ugly thing that happening to the receiver, and you got the data, but at some point, these data have to go somewhere, and you guys have to be able to use them to do data analysis. And that's when it gets also quite interesting, because typically when you are transferring the data to the server, no link in life is ever perfect, so there could be bytes that are dropped or packages that are not transferred. So the typical situation here is when you end up with for example, a 24-hour file that doesn't transfer, and then you have to retransfer it all. And depending on where you are, this is not only annoying, but it's also an expensive business. And I'm thinking about polar regions where you have maybe an iridium modem or stuff like that is slow and it costs money to transfer data. So we came up with a way to basically retransmit only the deltas that you have between what you have on your receiver and what you have on your server. And this is specifically and particularly useful when you have difficulties in your telemetry, but I can imagine that this is kind of nice to have in many more situations. So it's basically a fast differencing algorithm what we are using, and you end up really provided that, and I have a slide that shows which are the preconditions. You only end up retransmitting the data that have been lost, and just, for example, a gap, and the gap can virtually be everywhere. It could be at the beginning of the file or at the end, and that's the easy, but it could be also in the middle of your file. There are a couple of requirements to do that. That is, of course, that you have to have a clever, or well, maybe clever is not the right word, but you have to have the same file directory and structure at the receiver level and at the server level, and of course the same type of data logging and the same type of, so basically one has to be the mirror of the other for these to work. So this sort of completes, I mean, one thing is you get the data, and the other thing is you actually are able to have data to use. And these were more or less the two things. Well, I could speak for hours, but I know that I reached the 15 minutes. So I know, these are the two crucial things that we have made differently to try to help the community, and for which we are very, very happy to have any feedback. And I have 3 takeaways from this talk for whoever didn't know us before. Septentrio is a Belgian manufacturer of high-end GNSS receiver. Interference is out there, is a real threat, and we have a way to help you to visualize it and mitigate it. And we also can help you in optimizing and achieving data integrity with our receivers and algorithms. And with this, I thank you.